Welcome to another episode of Mr. Avila Physics. Today we're going to be discussing mass, weight, and normal force. Let's start talking about mass. The mass of an object refers to the amount of matter that is contained by the object. This is the number of atoms and molecules that make up that object. Now, if that object is moved to another planet or the moon or anywhere on the universe, the amount of molecules that make up that object will be the same. Therefore, the mass of an object is always the same, no matter where you are. In a previous video, we talked about inertia, and we talked about how mass and inertia were related. If we want to be more precise about what mass is the measure of the inertia of an object. So, the more mass an object has, the greater the force that we need to accelerate it. Okay? So, for example, if we compare a truck with a baseball, it's going to be a lot harder to get the truck to start moving from rest, or once it is moving, it's going to be a lot harder to stop it than a baseball. Right? So, since the truck has a greater inertia because it's more difficult to change its state of motion, then the truck has much more mass. Now, in order to have a universal measure of mass, we need a unit, right? And the unit for mass is the kilogram. Okay? Therefore, can we measure inertia in kilograms? No, mass is measured in kilograms, and the more mass that something has, the more inertia that object has. So the more massive an object, the harder it's going to be to change its state of motion. Now, let's talk about weight. We said in a previous video, in Unit 1, when we talked about free-falling motion, that all objects are attracted to the center of the Earth with a certain acceleration, right? And that acceleration is 9.8 meters per second squared. Now, since all objects accelerate towards the center of the Earth, there has to be a force that causes this acceleration. And that force is the force of gravity. And this force is referred to as the weight of the object. So, to rephrase this statement in a different manner, the weight of an object is the force of gravity acting on that particular object. Okay? So, if we say that if we want to apply Newton's second law to that, then we remember that Newton's second law is F equals ma. So the force is the weight, mass will be the same, and the acceleration due to gravity is g. So in order to calculate the weight of an object, we simply apply Newton's second law. And that becomes weight equals to mass times the acceleration due to gravity. Mass times gravity. Now, since the weight of an object is a force, then the unit for weight is newtons. Now, the difference than with mass, right? The weight of an object changes depending where this object is. The force of gravity or the acceleration due to gravity is different in different parts of the universe, right? For example, the acceleration due to gravity on the moon is 1/6 of that of the Earth. So if we take an object to the moon, its weight is going to be less. Its mass, however, is going to be the same. Now, there is another force that is very important in physics, and that is the normal force. The normal force is defined as the support force exerted upon an object that is in contact with another object or a surface. For example, if we place a book on a table, then the table is supporting the book and it provides an upward force on the book. So if we have something like, for example, if we have a table and we place a book here on the table, then the book doesn't fall off through the ground because the table is supporting it. So the book will feel a force of gravity known as its weight, but since the book is not moving, there has to be a force that is counteracting the weight, and that force is known as the normal force. So the book feels supported by the table, and that force would be the normal force. Now, sometimes the normal force is exerted horizontally, or sometimes the force is exerted at an angle. So if we're leaning against the wall, right, then we're leaning against the wall, so we're pushing against the wall this way, but we do not go through the wall because the wall pushes forward on us with a normal force, right? If we are on a ramp like this, right, then the ramp is pushing upwards on the book, right? And that would be its normal force. One thing that we do have to remember is that normal force is always perpendicular to the surface that is in contact with the object. So when two objects are in contact with each other, the normal force is perpendicular to that object, and in order to exist, the two objects have to be in contact. So if we look here, right, this person is horizontally sitting down here, so the normal force is straight up. Now this person, as it slides down the slide, the normal force is at an angle, but always perpendicular to the surface. If the two surfaces are not in contact with each other, then there's no normal force. This table is supporting nothing, so no normal force is there. All right, let's look at some examples. So a 10-kilogram box is resting on the surface of a table. Determine the weight of the box and the normal force exerted on it by the table. All right, pause the video here, take a couple of minutes, and see if you can come up with an answer. All right, welcome back. So here we have a table, right? And there is a book placed on that table. Now, since the book has a mass, because it's an object and it exists, then the book is going to feel a weight. It's going to feel a downward force towards the center of the earth. And since the book is resting on a table, then the table is supporting that book, and that is the normal force. Now, so here we can use Newton's second law. Newton's second law tells us that the sum of the forces is equal to mass times acceleration. The sum of the forces here are going to be the weight and the normal force. They're in opposite directions, right? So normal force minus weight is going to be equal to mass times acceleration. Since the book is not moving, acceleration is going to be 0. So that means that normal force minus weight is going to be equal to 0, which means that normal force is going to be equal to weight. So how do we find weight? Weight is equal to mg. So weight is going to be equal to 10, which is the mass, times 9.8, which is g. So weight is going to be equal to 98 newtons, which means that normal force will also be equal to 98 newtons. All right, let's look at this next example. the same 10-kilogram box is resting on the surface of a table. All right, so we have our table here. Oh, and now your friend is pushing down on the box with a force of 40 newtons. So here, my friend is pushing down on the box with a force of 40 newtons. Find the normal force exerted on the box by the table. Pause the video here and see if you can come up with an answer for this. All right, welcome back. So as we see here, right, we have the same book, right? The book has a mass, so therefore it has a weight, and the book is resting on a table, so the table is supporting the book with an upward force. All right. Now, using Newton's second law that says sum of the forces is equal to mass times acceleration, we see that, okay, we have normal force going upwards minus weight going downwards minus 40, which is also pointing downwards, and this is equal to mass times acceleration. Since the book is not moving, we know that acceleration is equal to 0. So then we have that normal force minus weight minus 40 is equal to 0. So normal force is going to be equal to weight plus 40, which means that normal force is going to be equal to, we had established that the weight was 98 plus 40, and this is equal to 138 newtons. So, as we see here, by pushing downwards on the book, we did not change the weight of the book, but now the table supporting the book has to support those extra 40 newtons. All right, let's look at this next example. So now the same 10-kilogram box is resting on the surface of a table, but now your friend pulls upward on the box with a force of 40 newtons. What is the normal force exerted on the box by the table? Pause the video here, take a couple of minutes, and see if you can come up with an answer for this. All right, welcome back. So here we have the same table, all right? We have the book resting on the table. The book has a mass, so it has a weight. The book is resting on a table, so it has an upward force, the normal force. And now my friend is pulling upwards on the book with a force of 40 newtons. So let's use Newton's second law again that says sum of the forces is equal to mass times acceleration. So here we have normal force plus 40 minus W equals mass times acceleration. So we see both normal force and the 40 Newton force, they both point upward, so they're both positive. Since the book is not moving, the acceleration is 0, right? So now we have that the normal force is going to be equal to weight minus 40. So normal force is going to be equal to 98 minus 40, which means that normal force is going to be equal to 58 newtons. Here, since my friend is pulling upwards on the book or in the box, right, then the table has to support less of a force. That's why our normal force is less. All right, let's try another example. So in this example, we have a 10-kilogram box is pulled by the attached cord as shown. Okay, the magnitude of the force is 40, and it is exerted at a 30-degree angle as shown here. Okay. So calculate the acceleration of the box and the magnitude of the upward force exerted by the table on the box. Pause the video here, take a couple of minutes, and see if you can solve this example. All right, welcome back. Now, the first thing we have to do is to draw the forces acting on this box. Now this box has a mass, so therefore it's going to have a weight. This box is resting on a surface, so therefore the surface is pushing upwards on the box, right, with a normal force, and this is being pulled at an angle. When you pull at an angle, you pull both horizontally, right, and you pull vertically. So you're doing two things at the same time, okay? So let's try and answer these questions right here. So to find the acceleration of the box, we will use Newton's second law. Sum of the forces is equal to mass times acceleration. Since we know that the box is moving horizontally, then only the horizontal forces will create acceleration. So that means that Fpx is equal to mass times acceleration. Now, Fpx is the horizontal component of the 40 Newton box. So using trigonometry and using SOHCAHTOA, we can find out that Fpx is going to be equal to Fp cosine of 30. So Fpx is going to be equal to 40 times cosine of 30. That gives me, hold up. That gives me 34.64. So Fpx is equal to 30.64 newtons, which means that 34.64 is equal to mass 10 times acceleration, which means that the acceleration is going to be equal to 3.46 meters per second squared. All right. Now we found the acceleration. The next question is asking to find the normal force acting on this box. So to find the normal force, I'm gonna delete this part right here, okay? So to find the normal force, we're gonna have to look at the vertical forces, right? So, well, we had the weight, we had our normal force, and we had the vertical component of the pushing force. So here we use Newton's second law, but we know that the box is not moving vertically, so there is no vertical acceleration, so I know that the sum of the forces vertically is going to be equal to 0, which means that normal force plus Fpy minus weight is going to be equal to 0. So normal force is going to be equal to W minus Fpy, which means that the normal force is going to be equal to mass times gravity, which is weight, minus Fpy, which is going to be equal to 40 sine 30. Right? Using trigonometry, I can see that this section is 40 times sine of 30. So that means that normal force is going to be equal to 98 minus 20. So normal force is going to be equal to 78 newtons. And here we found the acceleration and the normal force. All right. Let's look at this next example. All right, in this next example, we have two boxes connected by a cord, right? The boxes have different masses and they're both being pulled by a horizontal force of 40 newtons, okay? Let's find the acceleration of each box and the tension in the cord connecting the boxes. Now, when we have several objects, we can look at each object individually, or we can look at all the objects combined as a whole system. Okay, so a system is defined as any group of one or more objects that we examine together. Okay, pause the video here and see if we can find the answer to this question. All right, welcome back. Let's see if we can solve this. So here, the first thing we do is, of course, draw our forces acting on each of the boxes, right? So box B has a weight, has a normal force, it has a tension, right? Box A has a weight, it has a normal force, it has a tension going in this direction, right? And it has our forward force here. Now, the question is asking us to find the acceleration and the tension. So there are no questions about weight or normal force or anything like that. So let's see if we can find the acceleration of the box. So to find the acceleration of the box, I'm going to use Newton's second law, right? Sum of the forces is equal to mass times acceleration. Now, if I look at this whole thing as a system, then the only force that is pushing forward is Fp. So Fp will be equal to mass times acceleration. Now, since I'm looking at this whole thing as a system, then I gotta use the mass of the system. And the system includes both boxes. So this is gonna be 10 plus 12 times the acceleration. So that means that the acceleration is going to be equal to 40 divided by 22. The acceleration of the system is going to be equal to 40 divided by 22, which is 1.82 meters per second squared. Right? Now, when we look at the tension, we cannot see this as a whole system because the tension, if we see it as a whole system, the tensions will cancel each other out. So when we're trying to find the tension, we have to look at either box A or box B, whichever one we want. So I'm gonna erase this acceleration and solve question B. So to find question B, we're looking at the tension. So either we look at box B or we look at box A, whichever one we want. Now box B is going to be a lot easier. Why? Because we only have one horizontal force in box B. So if I look at box B, I'm going to say sum of the forces in B is equal to mass times acceleration. Now the only force acting on B is the tension. So tension is going to be equal to mass of B times acceleration of B, which means that tension is going to be equal to mass of B, which is 12, times the acceleration of B, which we just found, 1.82. That means that the tension is going to be equal to 12 multiplied by 1.82, which gives me 21.84. So 21.84 newtons would be the tension. All right. Hopefully these examples made sense and you know how to solve examples dealing with weight and normal force and tension forces. Thank you for watching. See you next time.